quantum numbers. Essentially, to describe the behavior of electrons we need 4 numbers. N is the principal quantum number, which is the size of the orbital. L is the angular momentum quantum number, which is the orbital shape. ML is the magnetic quantum number, which is the direction of the orbital. And MS is the spin quantum number, which is the electron's spin up or down. N starts from 1 and corresponds to the number of shells the atom has. This can be easily worked out for an element by looking at which row of the periodic table it is in. L starts at 0 and takes up the value to n-1. ML can have a positive and negative integer value, but its magnitude cannot be greater than L. MS can take the value of plus or minus a half, since an electron can only have 2 possible spin states. When L is 0, the shape of the orbital is S. When L is 1, it's a p orbital. When L is 2, it's a d orbital. And when L is 3, it's an f orbital, as the diagram shows. S orbitals are spherical in shape, but we don't have to worry about them. However, we have to worry about the shape of the p orbital, as they are a dumbbell shape. So when you're at the gym and you're curling away, remember a p orbital. There are 3 ml values, plus 1, 0, minus 1. Each ml value can have an ms value of plus or minus half. So each orbital has 2 electrons. So overall, p orbitals can hold 6 electrons.
D orbitals. There are 3 d orbitals. Therefore, n is equal to 3. Because n is equal to 3, this means L is equal to 2. ML is equal to plus 2, plus 1, 0, minus 1 and minus 2. Each number for ML represents 2 electrons. This means that d orbitals have 10 electrons in them. There are 5 orbitals pointing in different directions. This is because ML is equal to 5. These 5 orbitals correspond to dxy, dxz, dyz, dx squared minus y squared, and dx squared. These orbitals are shown here. The shaded teardrop shapes represent orbitals, and the lines represent the axes. The areas between the shaded areas on the diagram show there are no electrons in these areas, therefore there is no electron density. You must be able to draw d orbitals. It is easiest to draw them as 2 dimensions and change the axes as appropriate. The dashed lines on the diagram represent a nodal plane. A nodal plane has an electron density of 0. Shielding is a result of the electrons repelling each other and at the same time being attracted to the nucleus. The electrons closest to the nucleus will feel the greatest nuclear pull. Thus, as the electrons become further away from the nucleus, ZF will fall significantly. ZF is the effective nuclear charge, or simply the charge of the nucleus that is felt by the electron. Penetration describes the proximity to which an electron can approach the nucleus. In a multi-electron system, electron penetration is defined by an electron's relative electron density near the nucleus of an atom. The ability an electron has to penetrate depends on the shell. For example, electrons with the same value of n will have different abilities to penetrate depending on whether it is in the s, p or d orbital. Penetrating powers of electrons is shown below. On the left, the electrons are least shielded but have the most penetrating power, and on the right, the electrons are most shielded and have the least penetrating power.
We can use quantum numbers to work out how many electrons are in each shell. If we start with the shell n equals 1, then L can only be 0, and hence ML can also only be 0. This means that the only orbital in the shell n equals 1 is an s orbital. For this one s orbital, the value of ms can be positive or negative half. This means there are 2 electrons in the orbital, but that they must have opposite spins. If we take the shell n equals 3, the fact that n equals 3 means that L can be 0, 1 or 2. Each value of L has its own ML values. When L is 0, ML must also be 0. so we know again there is only one s orbital that holds 2 electrons. However, when L equals 1, the value of ml can be -1, 0 or 1. This means that it is a p orbital since L is 1. The fact that there are 3 values of ml means there must be 3 orbitals. If each orbital has an ms value of plus or minus a half, then 2 electrons can fit in each, so a total of 6 electrons can fit in the p orbitals. When the value of L equals 2, ml can be -2, -1, 0, 1 or 2. L being 2 means that it's a d orbital. Since we have 5 values of ml, there must be 5 d orbitals. Again, each orbital has an ms value of positive and negative half, so can contain 2 electrons each, so 10 electrons overall. This means that the shell n equals 3 has 2 plus 6 plus 10 electrons, which overall gives 18 electrons in the shell n equals 3. To work out for the n equals 4 shell, you would have to also include the orbitals that come with L equals 3. These are f orbitals. We can also use quantum numbers to identify electrons in an atom. Let's take carbon as an example. It has 6 electrons and its electron configuration is 1s2, 2s2, 2p2. You would follow the method just identified to find out which orbitals the electrons are in. But an important thing to notice is what happens to the electrons in the p orbitals. Since carbon only has 2 electrons in p orbitals, the electrons fill the orbitals individually. Electrons fill the orbitals with the same spin, as this produces less repulsion. Therefore, the 2 electrons in the p orbitals must have the same ms value. This can be either positive or negative a half for both of them.
The periodic table is organised in relation to the electron configuration. Elements are distributed into groups depending on the number of electrons in their outermost shell. Electron configuration shows how each energy level, which we referred to earlier on, is filled. For example, the electron configuration of carbon is 1s2, 2s2, 2p2. This means that the 2s orbitals are fully filled. The p orbital is partially filled. And this nicely leads on to talking about different blocks of the periodic table. The periodic table can be split into 4 blocks, the s, p, d and f blocks. Electrons are arranged into 4 blocks depending on which of their orbitals are partially filled. Group 1 and 2 elements can be found in the s block. The transition metals can be found in the d block. Groups 3 to 8 can be found in the p block, and the lanthanides and actinides can be found in the f block. Electron configuration can be worked out by using the periodic table. The position of the element tells us its electron configuration. For example, sodium can be found in group 1 of period 3. The period tells us its energy level, and the group tells us how many valence electrons are in its outermost shell, and also what type of orbitals are in its outermost shell. So the electron configuration of sodium is 1s2, 2s2, 2p6, 3s1. These rules can be used to find the electron configuration for the majority of elements. There are a few which are an exception to the rule, but the only 2 you need to know are copper and chromium. In these 2 exceptions, the 3d orbitals are partially filled, meaning there is 1 electron in each s orbital. This means that electron configuration for copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d9, as opposed to having 4s2. The next topic is the principles of the periodic table. There are 3 important principles to consider when looking at the periodic table. These are the Aufbau principle, Pauli exclusion principle, and Hund's rule of maximum multiplicity. First up, Aufbau. This principle says that each new period in the periodic table contains 1 more nuclear charge than the previous. This is done by the addition of a proton. The element stays neutral because as each proton is added, an electron is also added to neutralize the positive charge. For example, lithium has 3 protons, and the following element, beryllium, has 4 protons. The second principle is Pauli exclusion. This principle states that only 2 electrons can occupy a single orbital. On top of this, if an orbital does contain 2 electrons, their spin must be paired, 1 electron up and 1 electron down. The third and final principle is Hund's rule, which states that the ground state of an atom is the one having the greatest number of unpaired electrons. This can also be referred to as the greatest multiplicity. Orbitals of the same energy level have electrons enter them one at a time with parallel spin. Orbitals are only filled when all orbitals of the same type and energy level are partially filled. As a result, the repulsion between electrons is minimized because they are entering different areas of space, further away from each other. They enter with the same spin because this also minimizes the repulsion between electrons. Thank you.